I encourage you to return to the PDF of these lecture slides because they're very involved. You'll find them at my website, thresholdmodel.com. So we're going to look starting at J.J. Thomson's work on the charge to mass ratio of the electron. You see, quantization in general preceded quantum mechanics in the atom and the quantized charge idea of the electron. So when J.J. Thomson did his experiment with an electron beam deflected by an electric field that bent it over, and then he put a magnet to straighten out the beam and did calculations on it. So he was able to decipher the charge to mass ratio of the electron. So he was using the particle model to figure out the nature of charge. But he later did a beautiful experiment to suspend liquid drops and determine the actual charge, the electron charge. And but I claim there was an artifact involved in this, in that there's some gigantic number of charges involved to suspend against gravity, that it's a threshold, it's a ensemble effect that's going on that lets you see through what the charge is. And also there are surface charge effects, surface tension effects that will tend to quantize the charge as seen in this experiment. So what happened is he deciphered the correct value of the charge constant, and then they put it in here and assume that in free space that the charge is the same as in matter. And in many ways it is, but it's a subtle difference that you'll find later in my work that is part of the resolution of wave-particle duality. So soon after, let's see, that was 1897, the charge to mass ratio, and 1898 quantized charge. In 1900, Planck devised his great equation. He used that energy is proportional to frequency in an algorithm to generate the black body distribution over frequency. So they use this funny letter nu, so I'll use it in honor of Planck, which is frequency. So what happened was that Einstein in 1905 said, let's just use the particle model and have it equal to the kinetic energy plus a work function to escape the surface. And that's the correct equation, all right. But it implies that light shows up in this form, in a quantized form. actually, it doesn't have to be that way. You can have this energy as a function of the electron and not light. But everybody, most people, physicists assume that this is about the energy of a photon. So, but there were many who objected, obviously, to this idea of quantizing light into photons. In 1910, Lorentz objected to it strongly in a paper and ended up saying light quanta just won't do. In a translation, it sounds like that. And other people objected. But anyway, the next year I want to point out is in 1911, Planck came out with a loading theory where he looked at the energy of absorption that goes up to a threshold and can stay there. And he did a nice graph of it in his book. And so in order to understand this, it's saying the same thing as that his constant is a maximum. It's his idea of saying continuous absorption, and then when it emits, it's explosive emission. This idea is about saying that Planck's constant is a maximum, which means you can have less action than the maximum, and you'd still be able to derive the black body distribution. And that's what he did in 1911, using this construct. Anyway, later, 1913, other people objected to the particle version of energy, quantizing energy, and Sommerfeld and Debye came up with a derivation that revved up the electron before it escaped. The same idea, a loading theory. There were several names for this loading theory. Oh, I forgot Lenard. Lenard, after Planck, in 1901, he did the photoelectric effect. And he called, he was able to see that the escape energy in the photoelectric effect, the initialization of charge against a stopping potential, is proportional to the frequency of the light. So it was really a simple matter for Einstein to say, oh, well, that proportional constant is Planck's constant. So I really give credit to Lenard for the photoelectric effect. Almost the same equation as what Einstein did. So back to our timeline. Let's see. We're up to 1917 now. Millikan predicts the unquantum effect, essentially. What I did experimentally, I called the unquantum effect. It's where energy can absorb and store up, and then it only needs a small fraction of energy to then emit everything. So he considered it in a workable way, that there's a preloaded state in charge, the way it absorbs light. And so let's go to 1923. The Compton effect. Compton did these beautiful experiments where, again, he used the particle model where X-rays would interact with just about anything with charges in it, and the charge would be bounced off in his model as a particle, and the X-ray would be deflected and lose some of its frequency. And my point is, this all worked to derive the equation that fits the experiment using the particle model. And people thought, oh, well, light in the form of X-rays and gamma rays must be particles because the equation fit the experiment. In 1924, de Broglie did a derivation of his famous wavelength equation, and wavelength is Planck's constant over momentum, mass times velocity. The way he did it, he took Einstein's energy is equal to mc squared, and he took Planck's energy equal to h nu, and then said, let's just put them together. He took out of the Lorentz transformation, which is, let's see, it's a time is equal to the 1 over the square root correction factor of a time minus, it's something like this. And as far as I can tell, what he did is he took this term and said, well, that has the dimensions of time. So we have time is equal to, and then from this you could say what time is, and you can get this equation with c squared is equal to a phase velocity times a group velocity. And so he put these two equations together, and you can then derive his wavelength equation. Now I'm saying this equation is also wrong because of the way it was derived and where it came from. It was just the yanking of this part of the Lorentz transformation and not counting the gamma factor and a few other problems. What it implies is that the wavelength in the de Broglie equation is super c, that the wavelength is associated with a faster than the speed of light phase velocity, which implies that this wavelength is about a probability wave. It's used that way in textbooks and papers regularly to justify the probability interpretation of quantum mechanics. And I'm saying that this derivation is just full of problems, and we shouldn't be taking that as truth. But what fakes them out, so to speak, is that this equation works in experiment. So they think that the derivation is right. But you can have other derivations that come up with a similar equation without such implications. So let's go on. After de Broglie, what happened was Schrodinger in 1926, his great equation that is used to, when you do solutions to the Schrodinger equation, they're all just combinations of exponentials of sines and cosines kind of waves, and decaying exponentials or growing exponentials. So those are all you do to solve the Schrodinger equation, is use equations of that sort to see that they fit into the equation. But what's really interesting about Schrodinger is that in his text, in his first famous paper, he wrote what he thought was going on, which was that charge was about beats of his wave function. That there's his wave function, but that there's an envelope of it that beats. And in his discussion, he understands that the envelope of psi is the identity of charge. And that's the model that I use for charge. So Schrodinger actually beat me to it, so to speak. And but I had this idea ahead of time, and so what I was doing is looking back in time to see who had similar ideas as to loading theory and beats and threshold models, and I found Schrodinger and Millikan to say these things. Very soon after Schrodinger did his equation of his wave function, the definition of his wave function was reinterpreted by Max Born in the same year, and he turned it into the probability interpretation that everybody has since taken on as how to use the Schrodinger equation. But Schrodinger opposed this. Schrodinger wrote that he hated quantum mechanics and the way it was reinterpreted. 1928, the element of time in the photoelectric effect. A beautiful experiment by Lorentz and Beams where they were able to read the element of time in the photoelectric effect. How quickly does the photoelectric effect respond in terms of emitting current? What's the response time? So they found, oh, it was close to a nanosecond or maybe 3 nanoseconds. And but there were other times here. There were longer times. But what happened was the textbooks don't talk about the longer times. They only care about this shortest time of a nanosecond or two. And then they kept experimenting. Other experimenters did the same kind of measure. And all they cared about was what's the shortest time. And in our textbooks, it gives a false impression. They only talk about this shortest time as if it's the only time involved. It's just not true. The experimentalists had all these other times, and there are other reasons for extending the time having to do with a radio wave kind of focusing effect, the way antennas can be smaller than the wavelength of the radio wave. It happens with the atom also. So the derivation is all messed up that they used in our textbooks. I'll show you that later. 1930, the model of the photon was expressed in words, first by Einstein, and it's explained in a book by Bohr, where he's quoting Einstein to say, a photon will go one way or another at a beam splitter. Let's draw the beam splitter. And so whatever a photon is, it's not a blob of light. It's not anything localized at all. This is a phenomenological definition of what the photon is supposed to be, the photon model. And so it's supposed to make a click only in one direction or the other, but not both at the same time. If you have a one at a time source here, it'll go here or there. Now, part of that same definition is that if you were to reconverge the beam in like a Mach-Zehnder type of interferometer, that over here you'll see an interference pattern, a wave pattern build up. So for a wave pattern to build up, you have to have both paths. It doesn't happen with just one way or the other. Yet, that's the definition of the photon, that this will happen if you reconverge a beam and look over time. But if you look for just a short time, one or the other, you will see only one way or the other. And there's no way to understand that in terms of space and time, how that could be. That is what quantum mechanics is about. It's about this phenomenological model of what the photon should be. And so Heisenberg wrote about it, and de Broglie wrote about it in their books. And Heisenberg explains that it implies a collapse of the wave function over any distance, and people misuse that idea in all different ways. That is the idea of quantum mechanics. And people have been arguing against all this ever since the beginnings that I'm pointing out. That let's go on. So that was 1930. 1935, Millikan abandons the loading theory. He writes in his next book that it's terribly difficult to conceive. Now, Millikan did understand the idea of a preloaded state. He wrote it in his books. After this work of Millikan, everyone that talks about the loading theory or the accumulation hypothesis or the threshold model, whatever words you want to call it, they leave out the idea of a preloaded state that Millikan understood. Everything after this 1935, so I looked extensively everywhere I could find. No one talks about such a thing as a preloaded state. They do not treat the loading theory in a workable way at all. Also, 1935, it's in Max Born's book, where he describes how to mess up this idea of the loading theory, that there's no such way to see that it could load up. You can read this in my PDF. Please read the PDF of this lecture, because there's just too much material to see here in the video. In 1956, Bernstein and Mann wrote a paper where they collected the different experiments that were done by other people of the element of time in the Compton effect, and they also make the same mistake of only looking at how fast will the electron and gamma ray signature clicks in their detectors. How quick will that happen? What is the response time? In 1935, there was Einstein's paper where he came up with a model of an objection to quantum mechanics, where if there was something that happened in the middle with two electrons going in each way, that if there was a property in one direction and a property in the other direction, that since it's a probability wave, that the signature of its upness would happen at the same instant of time as the signature of its downness, irregardless of the distance between them, which implies that there's a faster than the speed of light kind of communication. But this is just a result of the probability interpretation. but still it was an important idea. And what I'm getting to is that in 1964, Bell did his theory where he'll use some particle-like equations to say what would be the relationship of coincidences, the number of coincidences versus the angle between those two events that I showed that separated on both sides of the lab. So the Bell theory predicts this kind of response, straight lines, because it's just linear terms in the Bell inequalities. So when Alain Aspect did this experiment, he was able to, he did an experiment that worked well. The experiment came out like this. Where there's angle versus the number of the coincidence rate. So the experiment and the theory had a discrepancy mostly at these points. And that's where they do the experiment. My point is that in this case, quantum mechanics actually has it right, where they have this curve. Now, what's important is that quantum mechanics equals classical mechanics in this case, and as it should. And that's the same thing as what Malice's law came up with about polarizers. And so, and this also fits the experiment. So the experiment and quantum mechanics and classical mechanics all agree on this. So who are you going to believe? Where all of that agrees and where Bell disagrees, I'm saying obviously there's something wrong with Bell's derivation. And what it's about, you'll find, is that Bell did not include this idea of a preloaded state in his derivations. And if you do that, I'm predicting that you'll get the experiment to fit the theory. So that's what the Bell theory and all that controversy is about. It's a raging controversy and people doing all kinds of experiments over it. Now we're up to 1972, where I'm going to show you in our textbooks the element of time in the photoelectric effect calculation where they mislead you. And you can look at this at your leisure to see what's going on. They make you, essentially brainwash you to think that there's no such thing as a preloaded state and that photons must be happening, that classical is not able to explain what's going on. It's very unfair treatment. Now we're up to 1985, where Feynman wrote a very influential book, QED, and he is so emphatic and so eloquent about photons. He was wrong about the photomultiplier tube. He didn't understand that in the pulse height distribution of a photomultiplier tube over frequency is a wide distribution. Like if you look at the strength of the clicks that happen, that they change in a wide way. So it isn't at all the way he described in his book. And that's a big problem in what happens in these tests that they do of the photon model, which was done by, at first it was done by Clauser. So Clauser did an experiment which was the same as this beam split coincidence test first described by Einstein. And he did it pretty carefully, but still there were problems in using polarized beam splitters and not understanding how photomultiplier tubes can have artifacts and delay times in them. And those problems in these experiments persist, where they are trying to say, when they test this one way or another property in the beam splitter experiment, that quantum mechanics seems to hold up. So I reproduced those experiments. I reproduced a version of that experiment using gamma rays, and I'm able to see through the illusion. I see the opposite result. So I'm able to call out their false assumptions. Another interesting experiment that I want to bring up was that in 1999 there was diffraction of helium against a grid of circles of ways that it was like a diffraction lens, where some of the heliums will go through as if it was a particle. They were particles that went through. But other heliums that went through diffracted and showed up. So if you look at the diffraction pattern, there's a big peak that happens here, and then there's a plateau where the actual particles go through. So what's interesting is it shows that in the same experiment you can have two different states of matter, the matter wave and it being held together as a particle, showing up in the same experiment. That's a big clue as to what's going on, because with wave-particle duality, it's not just that light has it. It's atoms and electrons and protons, neutrons, all that other stuff. And here, with helium, it has wave-particle duality. But with this experiment, you can still interpret with the probability interpretation that it's a probability wave as to whether it shows up here to interfere constructively as a wave instead of just simply as a particle. So in conclusion, what I want to say is that the loading theory is the most often argued alternative to quantum mechanics. And it's often misquoted and misunderstood especially in your textbooks. And that arguments for and against quantum mechanics are about the history of quantum mechanics. The arguments for and against quantum mechanics are the history of quantum mechanics. So let me also point out that there are different words for quantum mechanics and this wave-particle duality problem, and you can see them listed just so you have understanding of the different words. Thank you.